Hello everyone and welcome to today's webinar. Today's webinar is about the new AnyBody thoracic spine, ribcage and abdominal model. My name is Christopher Iversen and I work here at AnyBody Technology, and today I'll be the host of this webinar. In the AnyBody webcast series, we usually host presenters who have worked with the AnyBody modeling system to cover different use cases. However, in today's webcast, we have an internal speaker from AnyBody Technology. My colleague Hamed Shayestepur, who is one of our biomechanics specialists, and Hamed will present a technical overview of the new generic rigid body thoracic spine, ribcage and abdominal model developed in the AnyBody modeling system, and alongside with some practical examples such as scoliotic postures. And this model is already available on GitHub in AMMR 4.0, so if you are interested in using the model, it's surely possible to do so. The presentation will start in a few minutes or so, but just before we go ahead and start, I'll just give you a short general introduction and overview of the AnyBody modeling system, if there's any of you who are unfamiliar with the software or musculoskeletal modeling and simulations in general. So first of all, I would like to draw your attention to the control panel which appears on the right side of your screen. You are very welcome to submit questions and comments via the questions panel during the presentation, and we will try to address these questions at the very end of the webinar in a Q&A session. But in case we do not get to answer all of your questions, we'll try to do so by email within a reasonable time. So let's begin with having a look at what the AnyBody modeling system actually is. The AnyBody modeling system is a software that allows you to do musculoskeletal modeling and simulations, and as input it takes motion data as kinematics and forces. And it calculates the internal body loads as joint reaction forces, muscle activity, and metabolic energy. And at the moment, AnyBody is used in a wide variety of areas and applications. A few examples of this is movement analysis, product optimization design, the field of sports optimization, orthopedics and rehabilitation. It could be ergonomics with and without assistive devices as exoskeletons, and also in the automotive industry. And to give you an idea about the typical workflow in AnyBody, it could look something like this. So you provide the recorded motion data as input, and then you can use the body models which you or others have built. And then you can provide some kind of environment, which could be a special type of equipment, or for example, an exoskeleton. You can then use AnyBody to combine these things, solve the muscle recruitment, and run the inverse dynamic simulation. This basically means that we go from motion to calculating the internal body loads and also the interaction with the environment in some cases. You can then output the result and use it for some kind of post-processing, which could be with, for example, some kind of finite element tool. But there's also many users who close this loop completely by doing some kind of design optimization and then run this cycle multiple times. And this actually brings me to the end of the introduction, and I'll hand over the word and present the role to Hamed instead.
Hello everyone, I'm Hamed Shayestepur. I'm working in AnyBody Technology as an engineer. So in this presentation, I'm gonna explain the new thoracic spine and ribcage model that you can see in the left side. And maybe I take my pointer as well. And then with this new thoracic spine and ribcage model, you can specify any spinal alignment, and then the ribcage will follow. And also I'll explain a little bit about the new abdominal pressure model. So in the abdominal pressure model, you can the volumes can have pressure inside, and then the muscle should balance the pressure forces. So here's the outline. I'll give you a little bit of history of this study and the papers, and then I'll explain the new thoracic spine and ribcage model, which includes the spine drivers and the ribcage constraints, and then the new abdominal pressure model, a little bit about the layers and volumes that are inside the abdominal model, and then the new diaphragm and how the abdominal mechanism works. and then I'll show you some cases with some detailed muscle configurations, and then a few examples of bending spine, scoliosis model, and a little bit about the thoracic MOCAP model, and maybe a scoliosis MOCAP model if anyone wanted to use that. And then we go to the Q&A session. I've started my PhD in 2019 in Aalborg University, and my supervisor is Professor John Rasmussen. You probably know him. He's a really cool guy and very professional supervisor. And the funding was a Marie Curie grant. And then I continued the working on the same model in AnyBody technology from 2022, and we actually are working on it like as a team now. So it was a great work. So the papers some of them are listed here. So the first one is actually the previous version of the spine and ribcage model that is already published, but the rest are in progress. So the second one is the new thoracic spine and ribcage model. The third one is about the new abdominal pressure model. The fourth one is the detailed muscle configuration and some model validations. And then recently we actually submitted a nice and small abstract to a EORS conference, and we used the scoliosis MOCAP model to analyze some adolescent idiopathic scoliosis. So let's dive into the model now. So you can actually enable the new thoracic model using this definition. So it's a thoracic model flexible. And then in the new thoracic spine and ribcage model, we have new segments. So 12 thoracic vertebrae, 24 ribs left and right, and then 2 sternum segments. And the sternum segments actually are like, so they are divided with the manubriosternal joint that is right here. So how the model works. So the model is very easy to use, so we can just drive the spine, the posture of the spine, and then the rib cage is driven like by itself. So it's driven by newly defined averaging measure that I'll explain later. But the features of the model is that the rib cage is kinematically determined. It means that there is no need for extra input drivers. So when you drive the spine, the rib cage will follow the motion. So with this model, you can simulate detailed ribcage kinematics with a wide range of spine motion. It's very robust. You can do almost like whatever the spine alignment it is. And it's very easy to use. It's very beneficial for MOCAP models. And in the second paper, actually, we did some kinematic validations, and we compared the rib movements to the specimens that came from the literature, and we actually had some X-rays from some scoliosis patients, and we compared the model rib movements to those, and it shows a very good result. So how do we drive the spine? We have 12 thoracic vertebrae. So just like before, we have spherical joints between the vertebrae, like lumbar and cervical part. So this gives us 3 rotational degrees of freedom in each vertebra, which is 36 rotational degrees of freedom for all thoracic spine. And this is the only input that you have to put to the model. So when you want to drive this vertebrae, so you can use the implemented rhythms when you don't have data on all the intervertebral angles. So let's say you just know that, for example, the lateral bending is 30 degrees, then you don't have all the intervertebral angles. So you can just use the implemented rhythms. That will explain a little bit about it in the next slide. Or you can just define like traditional drivers, rotational drivers, and then you need to specify each intervertebral angle on that. So the implemented rhythms actually were explained in the previous webcast by my colleague Mortal Lund in the webcast called like new features in AMS 8. But I'll give you an example here to understand how it works. So let's say we have different regions of the spine, and then we want to simulate an axial rotation. So let's say we have some degrees and the total range of motion is 100%. So from the literature, we know that 10% of the axial rotation happens in the lumbar part, and then 30% in the thoracic part. So, and then here from the literature, we also know that each vertebra rotates. Like for example, this one is a little bit less than 20% of these 10%, and then we have all the data for all the way up to the C1. So what we can do is that Morten actually made a cool class template, so you can just take the measures here. So we have, for example, here we have the measures from T1 to T12, and then you can put the coefficients that you calculated based on the literature data that I just showed you. So you say that, for example, this one should be equal to this one, so they have the same weights, and for example this one has to move more, then it has a bigger weight, and then all the way down. And then you will have the rhythms, and the rhythms actually will constrain the spine in that part of the spine that you have to measure here. So you have to have the axial rotation, lateral bending, and flexion drivers, rhythm drivers for lumbar, and also for thoracic, and also for cervical. And this is what you have already in your model, so it's already enabled. So this leaves only 3 rotational drivers that you need to drive the model. So you just need the 3 rotational driver to drive the whole spine. So you say that, for example, 30-degree flexion or whatever you want, and then the model goes there. So enough about the spine. Let's go to the ribcage constraints. So the the hard part to get the ribcage kinematics work, it was that the complexity actually was due to multiple closed loop that forms this ribcage. So the ribcage, as you know, is a closed loop mechanism. So it was actually kind of hard to skip the redundancy and make the model kinematically determinate. But that's how we did it here. And also we had to note that it has to have anatomical joint definition, and it has to replicate pathological deformities correspond to clinical imaging when we compare them to the X-rays. So the constraints actually are The first one is that there is a spherical joint in the costovertebral joint node, which connects the ribs to the vertebra. And then we defined a completely new measure, which we call it averaging measure. This measure actually can be interpreted as physically can be interpreted as the static equilibrium position between multiple layer springs, and it's just for the kinematics. So let's say you have a segment on the air, and then you have some springs connected to that, and then when you release the segment, it will find the equilibrium position, and that's what this averaging measure do. But note that it's not springs, it's just the measures, it's linear measures, and it's just for kinematics only. It doesn't do any forces. And with this averaging measure, you can constrain a segment to multiple others in an average sense. So this can actually help a lot in these mechanism that we have closed loop. And then this measure actually comprises 3 linear and 3 rotational submeasures, which we can constrain those. So let's have an example here. Let's start with the sternum at the right side. So let's say we want to constrain the sternum, and it has 6 degrees of freedom. The blue nodes here are the nodes on the costochondral region of the sternum, and then the red nodes are the relative nodes, the same relative nodes on the ribs. And then the black arrows are the linear measures. So the linear measures between these two. So the averaging measure actually takes all these linear measures and make an average on those, and then find the position of the sternum, and it can constrain all the 6 degrees of freedom. So the cool thing about this one is that if you, for example, move some of the ribs, the sternum moves a little bit, but not too much, because it has the rest of the ribs as well. And then you can simulate a lot of things with this. You can cut some of the ribs, broken ribs, and a lot of things. So that's really beneficial. And then we have the same, we use the same concept for the rib here. Let's say we want to constrain rib 9. The rib 9, again, the blue nodes are on the ribs, the rib 9 that we want to constrain, and the red nodes are on the surrounding segments. So you can see the black arrows. So it has a connection here to the vertebra, here to the upper rib, here to the lower rib, and then here to the sternum. So the rib actually has a connection to all the surrounding segments. So when the surrounding segments moves, this one will move as well. So this is how we constrain the rib cage. Then with this constraints, the rib cage will follow the spine, so you don't need to drive each rib or sternum or whatever. So let's go to the abdominal pressure model. You can enable the abdominal pressure model with this definition. So it's a cavity model volume. So the objects and features in the abdominal pressure model is actually there are 5 moving layers, plus some pelvic layers that I didn't show it here, but you can see the 5 layers that are relatively in the same position of the lumbar vertebra. And then when you, for example, this is the standing, then this is the 50-degree spine flexion. So you can see that these layers can be squeezed. And then we have 6 deformable volumes. We made a new measure called Anikin volume seal mesh. So you can create volumes, and these volumes are able to hold the whole pressure. So, and these volumes actually made by nodes on these layers. So when the layers moves, the volumes will change as well. That's why we call them deformable volumes. And then, as I said, these volumes can hold the pressure, and then they can transfer the pressure to adjacent objects. I'll explain later a little bit about how they do that. But then another feature is that we are allowed to move the layers anteriorly, so it can create a belly and maybe simulate obesity or something like that. So about the abdomen constraints. So if you look at this picture, it has 3 layers, and then all the layers have spherical joints to the relative vertebra, which constrain 3 linear degrees of freedom. And then if we want to, let's say, constrain the rotational degree of freedom of this red layer, we use again we use the averaging constraint to find the layer position. So in this picture, actually, you see the red coordinates that are defined on the red layer, and then the blue ones on the top and bottom layer. And then again, these black arrows are the linear measures, and then the averaging measure use these linear measure to find the layer position. So it will be something between these 2 layers. And then we have in each layer we have 4 segments that are connected to each other with prismatic joints. I'm not gonna go through all the details of the like the kinematics, but this mechanism allows us to transfer the pressure through these prismatic joints, so it can push up and then it can push like anteriorly, and then the muscles will have to balance the pressure forces. And then you can see here that with these prismatic joints, the anterior part, it can move and then simulate the obesity when we have when we have them moved anteriorly in all the layers. So this is just in one layer. So when we have transferred the pressure all the way up, so we have the pressure on the abdomen, and then it goes up to the top layer. Here it comes the diaphragm. So with the diaphragm, also we have 4 segments, which all the segments constrained by surrounding ribs, sternum, and vertebrae. I also don't go through detail of the exact mechanism of this, but this mechanism allows to transfer pressure through the volume to the top segments, and then the diaphragm will actually hold these segments vertically, and then the diaphragm muscles will balance the pressure force. So let me explain a little bit more about the diaphragm here. So here you can see the sagittal view of the neutral position of the diaphragm, and here is the frontal view. And then the diaphragm can move upward to simulate inhale and exhale. So these 2 are the pictures of when it goes up. The red coordinates actually are the nodes on the diaphragm, and the blue coordinates are are the nodes on the surrounding segments. So you can see that the blue nodes doesn't move here, and the red nodes are up here. So one of the features of this model is that the diaphragm movements correspond to fluoroscopy movement. So if you see here, this is the back of the spine, and then this is the anterior part, and this posterior part, and this is the diaphragm that you see here. So the red one is the one when it's in the bottom, and then the yellow one when it's the diaphragm is and at the top. So you can see that in that anterior part it doesn't move a lot, but in the posterior part it moves much more, which is the same in the model as well. I may have moved the diaphragm too much here to the top, otherwise it will be almost similar to what you see here. And then another thing is that we have a very nice dome-shaped diaphragm with proper muscle wrapping, which gives us an evenly distributed force on diaphragm muscles, which is very nice because it will distribute the forces to the like ribs. You can see, for example, it has 3 insertions on the rib 10, and then to the rib 11 and rib 12, and also sternum. So it will transfer the forces to all of these lower rib cage. So how the abdomen mechanism works if we put all these volumes and the rib, the diaphragm together. So we have the pressures inside the volumes, so the pressure can build up inside the whole volume like this. And then we have the diaphragm at the top. It can hold the pressure at the top and transfer the forces to the lower rib cage wherever it has the insertion points. And then it results in an extensor moment to the rib cage, which is what we expected. And then we have the transversus, oblique muscles, and the rectus muscles. These muscles are wrapped on the layers that I showed you before. So they can, when they are activated, they can apply forces to the layers posteriorly, and they can create pressure and balance the pressure force. So this is how the abdominal mechanism works. So here I'll show you a little bit of what we have as new muscle configurations. You already saw the diaphragm muscles. So you can see here that the diaphragm muscles are actually activated here. And you can see that the colors are the same almost. So it means that the force distribution on all the diaphragm is evenly distributed actually, and it's very nice. And we have the new oblique muscles, because the new oblique muscles are wrapping on the layers, and then they can push and create the pressure, and mostly actually what they do is that they balance the rib cage somehow. And then we have the intercostalis muscles that enables us to simulate breathing. And there are much more muscle improvements in the model. I didn't show all of those, but these are like completely new muscles that I've showed you already. So let's go to show some examples. So if you want to start with the model, I think this is the best way. So you go to the examples, and then there is a thoracic model. You can take that one, and then if you take this one, you are and the rhythms are already enabled. So what you need is just to add 3 drivers to the whole spine. So for example, here there is these Fourier drivers, but you can just use a simple driver as well to the pelvic thorax extension, lateral bending, and axial rotation, and then you put the range of motion or the angles, and then there you are. You can have different simulations. And for example, I showed some thoracic pictures here. So you can see that, for example, when it goes to the left side in the lateral bending, it squeezes here, and then again to the right part. So the kinematics of the ribcage, you can see how it changed. So if you want to create a scoliosis model example, you can see that here we can bend the spine like this. So what you have to do is that you have to exclude the rhythms, and then this means that you have to go to the lumbar part and then exclude the flexion, rotation, and lateral bending, and then you have to do it for thoracic part, and then there are some links that link these two like lumbar and thorax rhythms together. Those called link drivers. You have to disable all of these, or you can just define the rhythm off, then these will not be defined. But I just wanted to show you how what are the rhythms. So when you exclude those, then you have to add some drivers to drive the spine, and then you can just take a simple driver and then do take the measures, like the extension measures of sacrum, pelvis, L5, sacrum, all the way up to T1, T2, and then do it for rotational, axial rotation, and lateral bending. And then there you have the spine drivers, and you can put an angle on those drivers, and then there you are, you have a curved spine. So I'll explain a little bit here about the thoracic MOCAP model. So with the thoracic MOCAP model, you probably need the thoracic model flexible, and then you have to put the rhythms as rhythms soft, so the markers can actually have effects as well. Otherwise, they will be hard constraints, these rhythms, and then use ground reaction prediction if you want. So the new markers we have is that we have 5 markers on the spine, and it depends on the data that you have. If you want the more detailed model, then you need more. I'll explain a little bit later about it. And then we have 3 on the sternum, but you can just exclude 2 of them and use 1. So what is different here is that we need to define something like this, spine marker single. So this will enable this code, and this means that we have on the axial rotation, we have somehow big weights. So 1 is almost like the same as markers, we can say. And then for the lateral bending and flexion, we have a very low weight of these rhythms. This means that we allow the markers to drive lateral bending and flexion extension, but not the axial rotation. And it's because that we only have a single markers here. So if you have a marker cluster here, let's say instead of 1, you have a marker cluster that is 3 here, so you can capture the axial rotation of this node as well. Otherwise, you can't do that, and then it's not gonna be a good model, I think. But it really depends on your model and what data you have and how much accuracy you want. Yeah. And then you can also have a scoliosis MOCAP model. You can actually use the rhythms as well, but again, it really depends on how your data is. So my suggestion is that you have to take off the rhythms. So you put the rhythms off, thoracic and also lumbar, and then we define a new set of scoliosis driver, which is exactly the same as the scoliosis model as I showed you. And then you measure the angles from X-ray or some data that you have, and then put it there. So what you need to do is that in the parameter identification, you have to run these with the high weights. So the markers actually will be optimized and the scaling will be optimized, all the things. But the spinal alignment will not change much because they have big weights. But then in the run analysis, when you want to run the analysis, you have to put a low weight on these. Then the markers will lead the spine alignment. So you have to try this and see how it depends also in your data quality and a lot of things. And then you have to be more careful when you adding the arms, because the scapula is actually connected on the multiple ribs now. Before it was just a rigid thorax, now it's multiple ribs that it can go through all of them, and then it's very important that you have a good quality of the marker data on the arms and also shoulder mostly. So you can follow this model development on GitHub. You can just go here and see the model. And thank you for your attention.
Thank you very much for the presentation, Hamed. And just before we go to the Q&A session, I would just like to say a few words about our online resources. So if you want to know more about AnyBody technology, then you can go and check out our website, anybodytech.com, where you can find different events, special dates, and also all of our previous webcasts. We do also have a community website called anyscript.org. This is for people using AnyBody, and here you will find multiple online resources such as our wiki page, several blog posts, and also links to our repository sites. It's also here our forum is located, so you can go and ask questions and get help from some fellow AnyBody users. Then I would like to highlight a few upcoming events. So we have 3 upcoming conferences. So if you happen to attend either the ESB conference in Edinburgh, the SOA annual meeting in Florida, or the EORS meeting here in Aalborg, Denmark, where AnyBody technology also is located, then please stop by our booth and let us have a talk about musculoskeletal modeling and simulations. And to end the presentation, I would like to mention that we maintain a publication list of papers using the AnyBody modeling system on our website. And this list recently reached more than 1,000 publications, so this is really a great place to go and get inspiration if you want to know what has been done with AnyBody within your industry or research area. And this actually brings us to the Q&A session, so I would like to thank you for your attention so far, and then I will read a few of the questions for Hamed.